This conference will now be recorded.
So very good evening, students. Today we'll be finishing this chapter of waves, and with this we are completing the syllabus. So we had already discussed about this Doppler effect a little bit. So there we have seen the apparent change in the frequency of sound when the source and observer and or the medium are in relative motion. That is called Doppler effect. So the apparent change in the frequency, this is actually called Doppler effect, and that happens when there is a relative motion between the source and observer, or source, observer and medium. Okay, because sound travels through a medium, it requires a medium, so medium also plays a role. Then in the last class, what we have seen, we have derived expression for the apparent frequency which an observer can hear when the observer is stationary but the source is moving. In that case, this is the expression. So this is the frequency which observer can hear, that is nu prime is equal to v by v minus vs, where v is the velocity of sound wave and vs is the velocity of the source, and nu is the original frequency of the sound emitted by this source, and nu prime is the relative or the frequency which is actually getting altered. Okay, then we have derived expression for the apparent frequency which an observer can hear. In this case, the source is stationary but the observer is moving towards the source. If that is the case, then the frequency of the sound which the observer can hear, that is v plus vo divided by v, where v is the velocity of the sound in the medium and vo, this is the velocity of the observer with which it is moving towards the source. Excuse me. So and nu is the frequency, original frequency of the sound wave which the source is emitting. In this case, the frequency will be more. Okay, in both cases, frequency is more. If the source is going away from the observer or observer is going away from the source, then the pitch of the sound will be heard less. Okay, that is what we have discussed in the previous class. So we have another situation when both, so we are going to derive an expression for the apparent frequency of sound wave when both the observer and the source of sound are moving. Okay, if both are moving, and for first case, let us say moving towards each other, and this I am considering that the medium is stationary now. So what I am doing now, I am going to derive an expression for the sound frequency of the sound that an observer can hear if both the sound wave, suppose both that suppose there are two cars, okay, there are two cars while they are approaching towards each other, they are ringing they are just blowing the horn. In that cases, okay, suppose two buses are approaching each other, okay, suppose this is the bus 1, just a minute. Excuse me. Okay, so I'm back. Suppose there are two buses, so which are approaching towards each other. The first bus and this is the second bus. I'm sorry, my son is. So this is bus 2 and this, suppose the bus 1 is actually blowing the horn when it is approaching towards the bus 2 and bus 2 also is approaching towards the bus 1. So they're approaching towards each other. So how the frequency of the sound will be for the passengers who are sitting in both buses, in case both buses are okay. So this is the situation. Now we'll derive the expression. What will be like, how we can find out the frequency of the sound heard by the observer. So let us say this is source and this is observer, and initially I'm just saying that this is okay. So initially they are in a position separated by, like in position separated by L distance, okay, so they are L distance away from each other. Okay, so I'm just considering the speed of the source is Vs, speed of the observer Vo, and speed of the sound wave is V. Okay, and let us say the time period of the sound wave is d, or 1 by frequency. This is the frequency, say this is the original frequency with which the sound wave propagates propagates when there is no relative motion, or this is the frequency of the sound wave originally produced by the source. Okay, so at t is equal to 0, suppose at t is equal to 0, that means just motion has been started for both of them. Both are approaching this way, okay, towards each other. The observer and the sound, they are approaching towards each other. So when t is equal to 0, they have just started approaching each other, or started their motion. Initially they have the length between, like separation between them is L, and since they are approaching towards each other with velocity vs and v naught, so what will be the relative velocity? V relative velocity will be the sum of these velocities, vs plus vo. Okay, so this is the velocity. So what is the time after which the observer can hear the first pulse of the sound wave? So as I said, at t is equal to 0, one sound pulse has been created or produced by the source, and both of them started moving at the same time. So after what time the sound wave will be heard by the observer? So that is the question. I'm sorry, this will not be okay. We are just going to get the relative velocity between the sound wave and the observer, because you are going to hear the sound wave, that's why. Okay, so relative velocity, I'm just writing in words so that, so the relative velocity between the sound wave and the observer is v relative is equal to v plus vo. So v means velocity of the sound wave, and vo is the velocity of the observer. Okay, so if this is the case, then what is the time after which the observer will receive the first pulse of the sound? So the time after which the first pulse will be observed by the observer is given by t1 is equal to L. That is the distance initially. And what is the speed? We know that the speeds are actually uniform speed or constant speeds. So we can write the distance L is equal to Vt, like that. So V relative into T1 will be this. So we can write this V relative. Okay, this will be L by V plus VO. Okay. So when I write nu and V, both are looking alike, but nu will be like this and V is like this. Okay, this will be narrow little bit. Nu, that is the frequency I'm denoting over here. Okay, so this is the time it takes. Now you go to the figure again. I'm just removing this. I hope you have understood this line. Okay, I'm little bit removing this part. Okay, so now suppose, see, one pulse it will take to complete, it will actually, after, see, since this is the frequency or t is the time period, after one full pulse is produced or sent, again another second pulse will be sent after this time period. I hope you are understanding. See, time period means the source of the sound is actually oscillating, and it has a time period of oscillation is t. Okay, so after sending first pulse, it will take t time to produce the another pulse. Okay, so by the time the source produce the second pulse, the source will move up to here. This is Vs into t. This much distance source will travel towards the observer, and observer also will move by this time Vo into t. So this much distance they will both travel towards each other. Okay, by the time the source produce the second pulse. Okay, second pulse. So it is the time period after which the second pulse will be produced, and during that time the source has moved from its initial position to another position towards the observer, that is Vs into t. So this is the distance it traveled, and the observer traveled Vo into t, this much distance. Now what is the distance remaining for the sound wave to cover, or the relative velocity? See, sound wave has the same velocity v. Now what is the relative velocity between the observer and this sound wave? That is the same actually, that is same. Okay, this is the relative velocity, but the distance is now different. Wave has to, or both sound and the observer has to travel to meet each other. Okay, then only the observer can hear. So let me write the new distance between the source and observer. So after t time, the distance between the source, sorry, distance between the observer and the source of sound. Okay, what will be that? Between observer and the source of sound is L minus Vs plus Vo into t. This is the new distance between the source and the observer. Okay, this is the new distance. Now we know that the relative velocity between the sound wave and the observer is, again, v relative is the same, v plus Vo. Then the time after which, so I'll write it, the time after which the second pulse will be received by the observer is given by T2 is equal to T after one time period, then the distance remaining, that is the Vs plus Vo into T divided by V plus Vo. So this is the time, the second pulse. Okay. After T2 seconds, second pulse will be hard. Then what is the time period? Therefore, the time period of the sound wave heard by the observer is T2 minus T1. So this is the time period, because see the gap between the two pulses heard by the observer will be the time period of the sound wave heard by the observer. So we can now see T2 is this L minus Vs plus Vo into T divided by, I'm sorry, this is this divided by V plus Vo, okay, minus L by V plus Vo. This is the T1. If you remember, I have written what is the T1. L by V plus Vo. Okay, so this is T2 minus T1. If we do the simplification, so this mathematical simplification, if we do, what we will get? See this part. If you see this part will get cancelled. Okay, and T is along with this. So let me write it. T into 1 minus, see this part is there, Vs minus, okay, let me go to the next page, better write here. I'll write again, time period T prime is equal to T plus L minus Vs Vo into T divided by, this is whole, divided by V plus Vo minus L by V plus Vo. Okay, see if we solve this, this will go like T minus Vs plus Vo divided by V plus Vo into T. Okay, if we take T common, 1 minus Vs plus Vo divided by V plus Vo. Okay, so now T into, if we just do the LCM and see, then it will be V, this V, one V will get cancelled, so V minus Vs divided by V plus Vo. Okay, so this is the time period. Then what is the frequency of the new wave? So I'll write here T prime is this one. So what is the new frequency? What is the frequency, apparent frequency the observer will hear? So that will be given by 1 by T prime. So we'll write that So this nu prime, that is the apparent frequency heard by the observer, will be V plus VO, okay, divided by V minus Vs into 1 over T. So this will be 1 over T, and 1 over T is the real uh, frequency of the sound wave emitted by the source. So this is nu. Okay, so this is the formula for the apparent frequency that the observer will hear. So we have got the apparent frequency of the sound wave heard by the observer when the observer and both the observer and source is moving towards each other. So what we have derived, see, if the source is moving with velocity vs and the observer is moving with velocity vo towards each other, and the sound wave has velocity v, then this is the formula. Apparent frequency heard by the observer will be v prime is equal to v plus vo divided by vs, v minus vs whole into the original frequency. So this is the formula we have got. I am just removing this part then, okay, because double writing will confuse you. So this is the frequency, okay. Let me do one thing. I'll write it here at this place, the same thing. I'm just rewriting because I need to keep this formula. Along with that, we'll do something else in this slide itself. So v is the velocity of the sound wave, vs is the velocity of the source, and this is the original frequency of the sound wave. Now look, now you might be thinking, sir, what happens if the medium also moves? Or let me, so this is actually the formula when both the source and the observer, both source and observer are moving towards each other, okay. But what happens if the source is moving towards the observer, source is moving towards the observer, but the observer is moving away from the source? Then what happens? What will be the change in the frequency? So this will be just in place of VO, you replace it with minus VO, okay. Then it will be actually decreasing, okay. Frequency will be decreasing. In this case it is increasing. So frequency, you have to replace VO with minus VO. So if I replace here VO with minus VO, velocity of the observer, this is velocity minus this into this. So this is the case. In that case, frequency, obviously, if I write this as double prime, so double prime is less than single prime. Okay, when both are moving towards each other, then the pitch of the sound or the frequency of the sound will be greater than when one of them, at least one of them, if see the observer is moving towards the towards the source and source is moving away. In that case also, in place of vs we can write minus vs. So in the denominator it will be positive. Okay. So in either case, the frequency of the sound wave will decrease. Okay. So we have got when the source is moving towards the observer with velocity vs, and observer is moving away. We got this case. Now look, in between there is medium also, right? If suppose medium has some velocity vm, and the medium is moving towards moving in a direction same as the velocity of the sound. If this is the case, then see, we'll write this triple prime. We had v minus vo divided by v minus vs, okay, into nu. We had this. Along with that, the velocity of the sound will be actually increasing. Velocity of the sound will increase by this much, okay? If the medium is also moving towards the velocity of the towards the same direction of the sound, okay, then v will be replaced by v plus vm, okay, v will be replaced by v plus vm, v plus vm, okay, and in the denominator also with the same thing, we'll write v plus vm minus of this. So this will be the case, okay, if the sound wave, sorry, if the medium is moving along with the sound wave, if it is moving in the same direction. But if suppose the medium source is moving this way, observer is moving this way, okay, sound wave is moving this way, but medium is moving, suppose the air is moving in the opposite direction, okay, then what will be the expression in this case? See, in place of plus Vm, we have to write minus Vm. So V minus Vm minus Vo here down, V minus Vm minus Vs. Okay, so this will be the formula in that case. Okay, so we have not almost, we have learned all the situations, and we have derived the expression for the frequencies, apparent frequencies. Now, maybe in the next class, we will take up numerical examples. Today we have few more things to discuss related to Doppler effect, just discussion. So it is said that Doppler effect is asymmetric. Doppler effect is asymmetric. What do you mean by this? Asymmetric. See, this is meant like say, I'm just picking up one situation. Suppose the source is moving towards the stationary observer. So what will be the apparent frequency? Suppose the frequency of the original sound wave is nu. Then nu prime, in this case, we have seen it will be how much? V by, sorry, if V be the velocity of the sound wave, and so V by V minus Vs. So this will be the apparent frequency. Along with that, original frequency will be multiplied. So it will increase. Anyway, this is the expression. Now suppose the source is stationary. So this is stationary. Observer is stationary. Now suppose source is stationary. That means Vs is 0. That time Vo was 0. Okay, stationary. And observer is moving towards the source. With the same situation, okay, same sound wave is produced by the source. Same distance, the wave helps to travel to be received by the observer. Suppose even the velocity also the same velocity as the Vs. Okay, suppose this Vo is exactly equal to the Vs, same velocity. Then also the frequency observed by the observer while it is moving with the same speed as the source towards the stationary source will not be the same. Look how it will be. V plus Vo divided by V into nu. So this Vo is exactly equal to Vs divided by V. Okay. So this will be the frequency. Are these same? I'm writing this is nu prime, double prime, and this is nu prime. So you can see that nu prime evidently, like clearly, these are not equal. Even though the situation is going to be similar, like say, at least expression should be V by V minus Vs. That should happen. Okay, so it is not happening. It is not happening. See, these are not the symmetric expression. So this is the case when the sound source of the sound is moving towards the stationary observer, and this is the case when the observer is moving towards the stationary source. So that's why Doppler effect is not symmetric in case of sound wave. Okay, why I'm saying sound wave? Is there any situation where there will be symmetric? Yes. For the electromagnetic wave, EM wave, it will be symmetric. Doppler effect is symmetric for EM wave. Is symmetric. Why it is and how it is, and why not for sound? Why not for sound? Because sound requires a medium. Sound requires a medium to travel. Okay, so that's the only reason. But EM wave does not require any medium. That's why it is symmetric. Where the source is moving, or the observer is moving, in both cases actually it will be the same change in the frequency. Okay, delta omega. Okay, change in the frequency. This is one case. Now we have seen where and how the Doppler effect happens. Okay, Doppler effect is observed. Now we'll discuss some points where or some. Okay, so where is or where does Doppler effect not occur? Okay, where does Doppler effect not occur? Okay, why doesn't Doppler effect occur? Okay, that means this change in the frequency doesn't happen in which cases? So first case obvious is when there is no relative velocity, relative velocity between the observer and the source. Okay, so when it happens, there is no relative velocity. Either both of them are stationary, source and observer, both are stationary. Okay, or one thing may happen if both of them moves in the same direction with the same uniform velocity. If both of them are moving in the same direction with same uniform velocity, then also this doesn't occur. Okay, relative this Doppler effect doesn't occur. Okay, and the third thing is when the source and okay, that I have already told. So these are the few points. So these are few points I have already told. Okay, so these are the cases where the Doppler effect doesn't occur. Now, one thing we have to learn, when observer is at rest and the source moves with a very, very high speed, that is the supersonic speed or the speed greater than the sound wave. In that case, a shock wave is generated. A shock wave will be generated. Like say if a supersonic jet plane just passes by, then we see a huge or a like kind of blast of sound, okay, that we hear at a sudden and violent sound. Okay, so this kind of wave is called shock wave. SHOCK, shock wave. When there is a huge sound at a time and suddenly we are hearing, that kind of wave is shock wave, like a jet plane is passing by. Okay, that is called shock wave. And there is another important term that is called Mach number. MACH, Mach number. What is this Mach number? Actually, the Mach number is the ratio of the speed of source to the speed of the sound. Speed of the source to the speed of the sound is called Mach number. Speed of the source to the speed of the sound. This is called Mach number. Mach number. So Mach number is given by this. So why do you need Mach number? Actually, shock waves are produced by objects moving with Mach number greater than 1. When the Mach number is greater than 1, then only shock waves will be produced. When Mach number is greater than 1, then shock wave. That means, see, the speed of the source is much greater than, at least greater than this. Okay, greater than the speed of the sound. Vs is the speed of the source and V is the speed of the sound. So greater than 1, then shock wave will be produced. Okay, shock wave will be produced. So this is all about this Doppler effect related things. Okay, Doppler effect we have completed the whole syllabus of this 11th standard, and today we'll be stopping it here. Next class I'll take tomorrow. Tomorrow we'll take classes on the numerical problems on this Doppler effect and few more things related to this waves chapter. Okay, so bye for today. Thanks for your patience.